All right, little thought experiment for you folks. Look up. So it says this. Note the readings on the scales. Left scale is reading 700 newtons. Right scale is reading 500 newtons. Burl the painter has a weight of 600 newtons, and he carries a 100 Newton bucket of paint. What does the weight of the scaffold have to be?
300.
Okay. What does the weight of the scaffold? It's not in your notes. This is a thought experiment. Stay with me here. Here we go.
It took me a second.
I know. That's why I told you. So, we have 600 newtons here. We have 100 newtons here. What must the weight of that be? Don't overcomplicate it. 500. Why? Is this sinking down into the, well, I can't say down into the ground. It's not on the ground. Is this accelerating down? Is it accelerating up? So the forces have to be balanced. Now, what are these two forces here? Those are tensions. Springs in ropes will measure the tension in the rope. So we have how many newtons pointing up, grand total? 1,200 newtons. How many newtons must we have pointing down if it's in balance, grand total? 1,200 newtons. So this has to be, it has to be 500 newtons. That's Newton's first law. Don't let the fact that there's a beam and it's still got to work. Still has to work. Today, lesson 8. Oh, mention bonus video game. That's right, Mr. Dewick. That's right. So I've mentioned the bonus video game. It's on my website. Lesson 8, various two-dimensional force problems. And what I'm really going to spend most of my time talking about here is what's called the lawnmower problem. In fact, I'm even going to be blatantly telling you there's going to be a lawnmower problem on the written section of your test. What's a lawnmower problem? Instead of being on a ramp, the ground is flat, but the force is at an angle. Did I say angle? What do you think we're going to try? Components. Okay? The reason we call it the lawnmower problem is if you ever pushed a lawnmower, you're pushing down the handle at an angle, but you're getting an acceleration straight horizontal. So, or you could pull up along the handle. Really what's going to be happening here, Taylor, is our normal force is going to be changing because we've got extra vertical components. So I wrote here the definition is where we have vertical force components other than normal force and mg. And in a problem like this, normal force is not going to be mg. Example 1 says, find the normal force, friction, and acceleration. I like example 1, except you know what? Probably for example 1 on your test, I would just say, find the acceleration, and I expect you to clue in that you have to find this other stuff. But if I was doing it on a test, I would do it like number 1. This is the level of difficulty, Ethan, where I stop taking shortcuts. This is about the point where I say, oh, I'm going to be really careful now. Okay? Let's be clever. Let's call this part A, part B, and part C. Kareem, what does part A want me to... Oh, before I even do that, Kareem, what should I be doing first? Let's label my forces. I noticed it looks like that 50 isn't quite touching the ground. That's my fault with the graphics. Pretend it is touching the ground. I see that there's a little gap there. Pretend it's not there. So, Kareem, what are the forces acting on this mass? Get the obvious one. Absolutely. What else? Normally, I would do normal force next, but because this one's going to be yucky, and I can tell it's going to be yucky because of that slanty force, I'm going to do the normal force a bit later. I'm going to deal with that yucky slanty force, and I've said slanty twice, which gives me my strategy. What am I going to do, Kareem, with this slanty force? Yeah. So I'm going to break it up into, I think you're pushing down and you're pushing to the right. I think it was Courtney earlier this year. I was yelling at you. You were doing your components and you weren't putting the arrows on, and I said you should. This is why, because now you can clearly see which way. What you can first of all see this is down, not up, and this is right, not left, and that makes a huge difference when you're doing your equations. Always put your arrows on your components. And you know what? Since this is horizontal, Kareem, I can call this Fy and Fx. If it was on a ramp, I'd go perpendicular and parallel. It's flat. Let's use y and x again. Kareem, is this sinking into the ground like quicksand? Is it flying into like Superman? What that really means is that everything up equals everything down. So the normal force has to cancel out everything down. Don't write this down. Why would I mark this wrong if you drew the normal force exactly the same size as mg? And I would mark that wrong. Why?
Force. Or I mean, vertical.
The normal force is going to have to cancel out both of those. I will be asking you to draw a free body diagram on your test, and I'll even be more blatant. The odds are pretty good. It will be a lawnmower question, and I will be fussy about arrow lengths. So here, I think the normal force has to be bigger than mg because it's canceling out both gravity and whoever's pushing down, Fy. Is that okay? Oh, by the way, if you wanted to, Nat, by the 200, you could put F applied, but here is my, beef is the wrong word. Here's my strategy. Is that 200 Marcus slanty? Well, then I'm never going to use it the same way as when we had a slanty velocity for a projectile. We never used that. We always used the components. So that 200 by itself will never appear in my equations. A 200 with a trig function next to it will. Cream, you okay with that?
Yeah.
Is there friction?
Yeah.
Which way do you think this mass is accelerating? Don't overcomplicate it. When you push on a lawnmower, which way would it accelerate? So which way is friction? Not sure how big friction is. I'll come back to that, but I got it there. Okay. Kareem, what's the first thing they wanted me to find?
Normal force.
Okay, normal force. I've always said, sinking to the ground like quicksand, is it flying? Really what I mean by that, Matt, is everything up has to be canceled out by everything down. So Kareem, can you give me an equation, everything up equals everything down, but using forces I have in my diagram? Everything up?
So when I say
Everything up? Which force is everything up?
normal force.
Equals everything down.
Mg.
No. No. Not mg. What's everything down? Eric, what? Yes? Yeah. What if instead of pushing down, because it's a handle, what if it was a rope and I was pulling up? Well, then that vertical component would be pointing up, and then I would have normal force plus Fy equals mg. And this is complicated enough, Prith, that unlike all the other times where I've said to you, oh, but look, now I'm going to say to you, you know what? Write a good equation to find the normal force. Don't try and intuitively do this in your head until you get really good. Now, I do have an equation for normal force, and that's what it wants me to find in part A. So, do I know M? Yeah, 50. Do I know G? Yeah, 9.8. Do I know F? Ooh. You know what? Let's redraw that triangle right here. Where this is 200, this is 20 degrees, this is Fy, and this is Fx. Kareem, Fy, opposite, adjacent, or hypotenuse?
Opposite.
Yes?
Yeah.
Okay, don't do that. Opposite. What about the 200? Which trig function can I use to calculate Fy? Yeah, and you know, this is complicated enough. I'm not going to take shortcuts. I'll write it out. Over here. I'm going to go sine 20 equals Fy over 200. How would I get the Fy by itself, my friend? Okay. Fy equals 200 sine 20, and I'll draw a little arrow pointing this way. So now I can write an equation for the normal force. It's going to be M, 50, G, 9.8, plus 200 sine 20. Michael, try typing this on your calculator just to make sure it's not a settings error, because this has got some trig to it. See if we get the same answer. 50 times 9.8 plus 200 times sine 20. I get 558.4. I'll write 558 to 3 sig figs, but I'll keep this on my calculator. Okay? So biggest, most common mistake. Okay, Dylan, you with me? Good, shush. Biggest, most common mistake that kids make, they glance at this and they do exactly what Kareem said. They go, oh, normal force equals mg. And I've tried to tell you this year, that's almost never going to happen. Certainly you can say this. If the question has an angle in it somewhere, whether it's a ramp, the ground is angled, or whether there's a force that's angled, hey, normal force is not mg. Or if you got more than one vertical force, if you've got any vertical force besides gravity, normal force is not mg. Be careful. Ethan, what does part B want me to find?
Friction.
Friction is what times what?
Mu times normal force.
And again, you don't have to have that memorized. It's on your formula sheet. But usually in this unit, kids have it in their brain. So, okay. What'd you say? Mu times what?
Normal.
And normally I would say, I don't know the normal force, but look. Here, I'm going to say, I don't know the normal force, but I would take the time to calculate the normal force because these are difficult enough that often I've had things pointing the wrong way and I'll plus when I should have minused or minus when I should have plussed or I'll do something silly. But conveniently, I do have the normal force. It's going to be not just 558, 558.4. What's mu? I don't know. What's mu with you? Oh, there it is, 0.1. Times 558.4. I can do this in my head because timesing by 0.1, that just moves the decimal point over one spot. But I'll do it on my calculator because I'm going to want this answer later on anyhow. I get 55.8 newtons. That's friction. You okay with that? Okay. I'll pause for a second. Have I done anything really new so far? I would argue probably not, but you can see I'm being way more careful here because this is a new situation. Dylan, what's part C want me to find? What's the last thing you want me to find? So we have to look at this and we ask, who's winning? Who's winning? The 200 is not winning. I said I'm not going to use the 200. Don't you dare say the 200. It's a slanty. We don't. And by the way, you can see I was queued up, ready to go on this rant because someone always says that, and I always go ballistic and say no. We don't have to use a slanty. Which way is this accelerating? So, Fx. Are there any other forces pointing to the right forwards? If there was, they would be winners. But for now, my equation's going to be winner. Any losers? Friction. And that's going to equal MA. That's going to equal MA. I guess that means the acceleration is going to be Fx minus friction over mass. Thankfully, Courtney, friction, I just figured out, it's 55.8. In fact, I have it stored on my calculator right here. What about Fx? Let's go back up to our triangle here. Dylan, come back light. That dimming is lasting a tiny bit longer each time, isn't it, when it flickers? I'm a little worried. Fx, you're saying it's adjacent? And you're saying of course it is? Yeah. Okay. So I'll take that shortcut. So if I hear you, you're telling me it's going to be 200 cosine of 20 minus, I'm going to write 55.8, but I'll use my answer button because I have that conveniently stored, divided by, mass is 50? Okay, bracket 200 cos 20, close off the cos, minus answer button, close off the top, divided by 50. What if I got a negative answer here? What would that be telling me? I got to be careful. No. Because friction doesn't move things for you that way. All it would be telling me is it's still at rest. You haven't overcome friction yet. You haven't overcome friction yet. Okay? I got to be fussy, right? When you tug on something, if it doesn't move, it doesn't go shooting back in the opposite direction. But that's a possibility. Here, positive answer, 2.64. Yes? Meters per second squared. Before we turn the page, How could I kick this up a notch? Well, I guess I could give you the acceleration and have you figure out how big friction had to be, and therefore have you figure out how big mu has to be. Like I could reverse engineer this whole question. Be tougher, but doable. Okay. So these are lawnmower questions. Let's do another one. What do I mean by a lawnmower question? Flat ground, force at an angle. Only here, instead of pushing down along the handle, here we're lifting up along the handle. What's that going to do to the normal force? Make it bigger, smaller, or the same size as mg? Smaller. Okay, I'll be really careful because by far, the most common mistakes are with the normal force. Second most common mistake, kids use the 200 instead of the horizontal component. Or in this case, 18. You know what? It says a force of 18 newtons. Let's put the 18 newtons on there. I like example 2, I like example 2, I like example 2. In fact, Taylor, although I said I like example 1, not probably, if I gave you this on a test, the odds are very good that I wouldn't walk you through part A and part B. I'd just say find the acceleration. Now here, I carefully went through part A and part B. I'll show you here. We'll try and do this in one fell swoop just to show you it can be done. I would probably, Sarah, do it that way in the homework. On a test or a quiz, I'd be way more step by step because there's plenty of room to make mistakes. But let's push the envelope a little bit. How am I going to start? Let's label the forces. What are the forces acting on this? Get the obvious one. Hello, pen. Come on. Okay, hang on. Got a dead spot right in the middle of my screen that irritates the heck out of me sometimes. There we go. mg. I'd like to do normal force next, except is there a slanty? I'm going to hold off on the normal force. I'm going to take that slanty. Did I say slanty? What's my strategy going to be? Components. So I'm going to break it up into fx and fy. Why would I mark this wrong for normal force if you drew it the same size as mg? Why would I mark that wrong? Sorry? Yeah. Oh, yeah. It'd be flying into the air like Superman. By the way, Michael, that's the other reason that I keep this angle really small, because if this angle was like 80 degrees, you might actually be lifting up enough to get it off the ground, and that would really change the question. So you're going to see in almost all the questions, it'll be 10 degrees, 12 degrees, 20 degrees. We're going to keep it pretty flat. Okay. Why would I be flying into like Superman? Because Fy is already pointing up, and so really the rest of the normal force has to cancel out what's left of gravity. I would look for a normal force that was clearly shorter than gravity. What else? Is there friction? Which way am I going to point friction? Well, which way is this thing likely accelerating? To the right. So let's point friction to the left. What if it wasn't moving? What if I told you it was at rest? How long would I draw the friction arrow? Exactly the same length as which force? Fx. I mean, there's a lot of good depth we can go into here. Okay. They want me to find the acceleration. Who's winning? Who is winning? Not the 18. Fx. Who's losing? Are there any other forces in the horizontal direction at all? I don't see any. Don't be putting that 18 in there. What does winner minus loser always equal? MA. If this was a test question, this would probably be worth 7 marks. I'd give you 1 mark for that. I'd give you 1 mark for getting the A by itself. Fx, let's do a little trig. Looks like in my diagram the 18 is the hypotenuse. Fx, opposite or adjacent Adjacent? Which trig function? A and H? Cos. It's going to be cos. Okay. So if I wanted to try and do this for homework and skip some steps, if I was doing it on a test, I would probably redraw the triangle and do the trig carefully, like we did last question. But I think it's going to be 18 cos theta, 21, minus mu times the normal force over m. I don't know the normal force. Okay. This is probably tough enough that I'm going to go off into the margin and write a vertical force equation. What do I mean by a vertical force equation? Everything up equals everything down. Everything down equals, what's everything up? Yes. So I guess, are you with me, Prith? The normal force this time is mg minus Fy. I think in the last question it was mg plus Fy, and that's because we were pushing down? Okay. Okay. So I can say this. The acceleration is going to be 18 cos theta minus mu bracket mg minus Fy all over m. Why are you using square brackets? Honestly, just to make it stand out more? I don't know. Do I know mu? Did they tell me?
Yeah.
Do I know m?
Yeah.
Do I know g? 9.8. Do I know Fy? Ooh. Huh, let's go back. Fy looks like it's opposite. Which trig function? So just to be really paranoid over here, I'll go sine 21 equals opposite over hypotenuse. How would I get the Fy by itself? I think times by 18. Okay, now I can plug everything in. I think. The acceleration is going to be 18 times the cosine of, what was theta? 21. Minus, what was mu? What's mu? I don't know. What's mu with you? 0.23. Bracket, the mass is 7 times 9.8 minus 18 sine 21 degrees, all divided by 7. The mass doesn't cancel here, which makes sense. When I push something, if it's heavier, it is tougher to push. If it's lighter, it is easier to push. And again, this one, Michael, is one for you to try. Did the other one work? Yeah. Okay, yeah, it's got to be a calculator typo. Bracket 18 times the cos of 21, close off the cosine, minus 0.23 times bracket 7 times 9.8 times 18 sine 21, close off the sine, close off the square bracket, close off the top, divided by 7. Oh, I typed this in wrong. I must have. What's the mass? What am I wrong on? Oh, right there. I did a times instead of a minus. It's not times 18. It's minus 18 sine 21. That'll make a difference. You get 0.359? No?
I did.
Anybody else get 0.359?
I got it.
Few of us? Okay. I think that's right. Okay. It's accelerating, but barely. Is that all right? Static equilibrium. We're going to finish with this question. I'm going to skip the next two, and I'm just going to give you lots of practice. And I got a cool video to show you, too. What's the definition of static equilibrium? When an object is at rest. And if you know it's at rest, what does that tell you about the acceleration? John, and what does it tell you about the forces? The forces are, I'm looking for a word that begins with the letter B. Okay? Example 3. I don't like example 3 in that it's not going to be on this test. I'm sneaking in a preview of a unit that I'm hoping to get to at the end of this year called static equilibrium. I'm not sure I will get to it. We're going to see. But just to let you know, we can handle at least this. What does it want us to find in this question? Marcus, what does this question want me to find? Tension. How am I going to start, do you think? How have I started pretty much every forces question? And I'm going to give you a little trick. For these questions, label the forces on the connection point right there, not on the mass, because the ropes actually aren't touching the mass, all of them. What are the forces acting on that connecting point? Get the obvious one. And then I'm going to call this tension 1, and I'm going to call this tension 2. Okay. Are there angles? So? You're right and wrong. Yes, and if you do this with components, it'll work. In fact, the component method works for pretty much anything. It's not always the fastest method, and I'm going to choose this time not to use components. Instead, I'm going to use vector math. How do I know to do that? Patience, and I'll show you. How many forces are there in this question here? 3. You know what I'm going to do? I'm going to add these together, tip to tail, tip to tail, tip to tail. I'm going to draw a vector shape. With me so far? Trust me, this will work out nice. I always start out by drawing the easiest force, the easiest vector first, gravity. That gives me a good frame of reference. So over here on the right, do a great big mg down. I'm going to add the next vector to it. How do I add vectors together? Draw them, tip to tail. And the vector that I'm going to draw next is the toughest, the ugliest, the most difficult vector. I think the slanty. Okay? And then just watch. See if you can tell me when I have to stop drawing this vector. Okay, that's too far because if I now draw the third vector, what do you know about that third vector? It has to be based on the picture exactly, looking for where it begins with the letter H. Horizontal. So if I drew this too long or if I drew this too short, that third vector can't be horizontal. So I know, that's why I draw the toughest one second. I know I'm going to stop right about there. There's tension 1. And the reason I know that is the third, and I'm going tip to tail again, the third vector, the second tension, from the picture is dead horizontal. By the way, if this was a displacement and I end up back where I started from, what's my displacement as a number? 0. These are forces. And I ended up back where I started from. What's my net force as a number? 0. They're balanced. And that's the only reason why, the fact that the forces are balanced, I can do this, which is going to be faster than components, because now I have a lovely right angle triangle. Marcus, you'll agree with me that 35, I think, fits in right there, because 35 is between a slanty and a vertical line. Marcus, that mg, opposite, adjacent, or hypotenuse? Yeah. Little different. All the other, for the ramps, mg was always the hypotenuse. Not here. In fact, the hypotenuse is tension 1. Yes? And tension 2 is the opposite. Let's solve for tension 1 on the left. Which trig function can I use, folks, to solve for tension 1? mg is the one that I know. So cos, and I'm going to be a little bit more careful because this is a weird triangle. So I'm going to write everything out. Cosine of 35 equals mg over tension 1. Yes? Adjacent over hypotenuse. Where is the tension 1 right now? How can I move it to the top? Times it over. And then what can I do with that cosine? Divide it over. I guess tension 1 is going to be mg divided by cos 35. 10 times 9.8 divided by cos 35. I'll call it 120 newtons. 119.6. I'll go to 3 sig figs. 120. Tension 2, which trig function? By the way, I guess I could use Pythagoras to find tension 2, but then I'm using an answer to find an answer, and I'm not wild about that. And I don't think it's any faster than doing trig. Tension 2, which trig function has the O and the A in it?
Fine.
Sorry?
Ten.
Why not use the mg again, right? You could with sine and use tension 1, but if you get tension 1 wrong, you're guaranteed to get tension 2 wrong. I'm a better test writer than that. So I'm going to use tangent. Tangent of 35 equals opposite over adjacent. Oh, how would I get the tension 2 by itself? Times by mg. Yes? So tension 2 10 times 9.8 times tan. I haven't pulled out tan for a while. Tan of 35. $68.6. Is that right? People nodding. Newtons. I did that because it fits in with what we've done. It's a nice time to do a preview of coming attractions. I'm not going to ask you that on the test. Example 4 actually was the instructions on how to do example 3. I keep forgetting to delete example 4 because I did it up there. And we're going to skip example 5. We're going to skip example 6.
So this won't be on the website.
Will not be. And what I assigned my block A's for homework is as follows. I got to give you lots of practice with these. Sorry. 1, 2, 3. Seven. 11. There's a lovely lawnmower question. 12. 14. 15 and 16. Hang on. Okay. 12, 14, 15, and 16. I was going to try and fit in a couple of more of the Shaolin Monk videos today. I'll bring them out next class. Next class, your homework is going to be a big take-home quiz on everything, and you can start working on the ultimate review. As of today, technically you can do every question from the ultimate dynamics review if you want to get a head start on it. Okay, but I'll give you the rest of this class to work on the homework.